Okay, let's start. So it's my great pleasure to introduce Craig today. Craig and I go back a long time because I met Craig when I moved to Canada to do my PhD here because he started his grad studies at the same year that I did. So there are few people here in Canada that know me better than Craig. Um, and Craig, so he did his master's and PhD here at the University of Alberta, and then he joined Sony AI, and eventually he decided to move to the other side of the world, and he lives in Tokyo now. And one thing that I find cool about Craig, and I always like work with Craig, is that he's one of those people that are very careful about how they do things in a way that I was never afraid of having a bug in his code because he was just like he wanted to understand everything that was going on in the pipeline, and I think that's a very good skill to have. So, but yeah, Craig, please take it away and talk about the work that you've been doing recently.
Thank you. Okay, so you started recording?
Sorry.
You started recording? Okay, and everyone online, can you hear me? Matt, you pipe in there? All right. All right, let's get going here then. So, let's figure out how to switch my screen. There we go. So today I'm going to talk to you about two areas of research I've been involved with at Sony AI. One is GT Sophy. This is an RL-based agent that we trained to race in the Gran Turismo video game. And the second is a technique we developed called value decomposition for this kind of iterative design of RL agents. So those are the two main works, but I'm going to harp on one kind of topic throughout this whole talk. So recently, Rich made the statement, not defining where the rewards come from kind of defines the field of RL. And this is kind of a consistent thing I've heard from Rich for a lot of years. Where do rewards come from? Don't worry about that. They're just given, and we can just use them. For those of us who do applied RL, rewards are really, really important. And I really want to get that across to you. If you forget everything else from this talk, it's that reward design is a really important and difficult and understudied problem. And I'd love for more people to care about it. So Sony AI's goal is to unleash human imagination and creativity with AI. We are a global research institute with offices in Tokyo, Zurich, Barcelona, Mumbai, and Boston. And we have a remote team in North America that does work on games, so AI for games. I am part of that games team, although I am based in Tokyo right now. So let's talk about Gran Turismo. See if I can get that to play. Oh, sorry. There we go. So while we're streaming the video, okay. So Gran Turismo is billed as a racing simulator, not just a game, but a simulator, and that means that they've paid a lot of attention to trying to get the physics, as good as they can. So high fidelity. So I'm showing you this video. On the top, that's in-game, and on the bottom is the same track in real life. And what's really cool about this is this driver, Ken Chan, he went out, he tuned his car in a particular way in the game, tuned his car in real life to be close to the same settings, went out and raced this track and was able to get lap times that were within 0.1 seconds of each other, just kind of attesting to the high fidelity of this game. Maybe some of you have seen this movie, Gran Turismo, that came out a few years ago. A really cool movie based on a true story. And the idea was there that they took gamers who had grown up playing Gran Turismo and were able to train them to then play real racing games, or drive real racing cars. Okay, so I get a little break while you watch this promo video about GT Sophy.
There's very few places where you can go out and say, I'm going to build an AI and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Gran Turismo Sophy is a super exciting project. It's an amazing AI research and development activity.
There are many racing games where the physics is half done, but in Gran Turismo, that racing sensation that the players get, that's really at the core of the game.
このなんか車文化、車という存在をもう丸ごとビデオゲームの中にこう再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophy agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースしていきたいなっていうふうに思いましたね。
Putting mic on now? Is that any better? Okay, so this work was done as a, this big team effort to put this together. We had people from, management, obviously. We had engineers and research scientists. We had interns that worked on this. And it was a partnership between three entities: Sony AI, Polyphony Digital, which is the game company that makes Gran Turismo, and Sony Interactive Entertainment, who's in charge of PlayStation. So the problem that we were given is that existing AI drivers in these racing car games, they're pretty boring actually, and they're not that capable. So when you start out playing a game like Gran Turismo, maybe it's your first time, they seem really challenging, but players can very quickly outrace these built-in AI. And then they don't really provide a fun game or an interesting way to kind of continually improve your skill. So we were challenged to fix this. And our solution was to train an agent using reinforcement learning that would outrace the top human players. So I'm going to come back to the technical details a little bit and just kind of right now just focus on kind of the high-level overview of what we've done. So we went out, we trained this agent, and then we set up these exhibition events. So in this, we were going to race against the top Japanese players in the world. This was during COVID, so we couldn't actually do the top players in the world, but just those in Japan. We had 3 tracks, each with a specific car, and we let the drivers know ahead of time what track and what car we would be using in these events. Each race was done as a 4 versus 4, so there would be 4 of our AI agent and 4 humans against each other. And scoring that was done based on the finishing position of each race. And then they would be scored as humans get 1 score and AI gets another score. And in October 2021, we won. We beat the humans. But if you look on this right column, you'll see that there's a July 2nd here. So the October, when we finally won, that was actually our second attempt. In the first one, we did not win. And there's an interesting reason why, or one. There were certainly some technical challenges that we overcame between those 2 events, but one of them was addressing a difference of expectations that we had. So as the designers, we were really thinking about each car out there racing to the best of its ability, trying to win, that all of the drivers would race this way. But if you recall the way I set it up, that we were going to have 4 humans versus 4 AIs, it was humans versus AIs. The humans didn't interpret it that way. They saw it as a team event. And so when they came out, they raced as a team and they blocked out Sophy from making passes and this kind of stuff. And they really dominated. But Sophy has no information about teams or anything like that. So one of the keys to making sure that we won in October was just communicating to the drivers and saying, hey, this is a situation. We need each of you to go out there and race to the best of your personal ability and try and get the best position that you can. And we got a nature paper for it. nice nature paper. It covers quite nice. So we moved on from there. This is still an ongoing project. It is now a product. And our new objective was to make an agent that is fun for everyone. So some things that we are not doing, though, is we're not optimizing over user metrics. What we are doing instead is working very closely with the game studio to make sure that the behaviors that we're producing with Sophy are matching what they're looking for. There have been some practical challenges in moving from the kind of exhibition event to getting it on the PlayStation 4 or 5, sorry. One is that it has to fit on the PlayStation 5, and we don't have access to the GPU, so it has to be a very lightweight model that we can use. It also means that we can't use things like vision, so we have a special API access that lets us get game data, game state out of there. We have a bit of a problem of shifting dynamics. So the game is being continually updated. So every few months, there might be a new release, a new update to the game. And when that happens, quite often the underlying physics can change. And this means that we have to throw out baselines that we had before, data that we had before, and start again. There's definitely been a difficulty in converting this new objective to reward functions. What does it mean to be fun for everyone? What does it mean to be human-like with these things? And we designers at Sony AI, we are not the ground truth on this. And so we have to work very closely with the game designers to make sure that what we develop matches their expected behavior. Some practical things too is that training an agent takes about 2 weeks before it's ready for release. And this means that when we are trying to make some sort of intervention, I've got a new tweak to the algorithm I want to try out, it takes at least 2 weeks to get results on that to figure out if it had the intended effect. And we have what I call the burden of success. So this is just more of a reflection on what it means to move from, kind of a demo thing to something that's a product. We have this whole stack of software now that's been built around GT Sophy. And that comes with a lot of technical debt and a lot of things that we're hesitant to really change. We don't want to break things. We want to keep things moving forward. So that means that when we make changes, we tend to make them incrementally, even algorithmically. We don't make big changes in the algorithm right now. We just kind of iteratively make small changes to get them out the door. As of March 2025, GT Sophy 2.1 was released. And this allows you to play with GT Sophy on over 400 cars and 22 tracks. So one thing I didn't mention is that in the original exhibition, it was 1 track, 1 car is 1 policy, 1 train policy. And so now we've been focusing a lot on generalization. And so now we can have 1 policy that plays over many different scenarios. So now I'll go into some of the technical details. I'm not going to go too deep here, but I'll give you an idea of some of the important parts. All right, so we are doing reinforcement learning. That means our AI agent, in this case GT Sophy, interacts with its environment, which is the Gran Turismo video game, and it gets observations about the video game as state, and it takes actions and gets a reward. And its goal is to learn a policy that maximizes the future reward, or the expected sum of future rewards. We use a pretty vanilla soft actor critic algorithm here. We did make a few small changes. We're using quantile regression on the critic heads. So that means instead of just getting the expected value, we are getting the distribution of the value and then converting it to the mean. The only reason we did this is because empirically it worked better. We also used n-step returns that allowed us to get better lap times and better overall performance. And our model is very simple, certainly at least at the time of the exhibition. So we just have 4 layers of 20, 40, 80, 48, sorry, with ReLU activations. Yep.
What's the value on the graph?
That's lap time. Yeah, so just, I mean, it probably looks fairly trivial. You know, got 115.9 at the worst. The one we picked, we end up using n equals 5, so 114.4. That's really big difference in racing there in a lap. Yeah. I don't know. That was not part of, I was not part of that decision process. One thing we did that's a little different than the original SAC is that we're doing asynchronous SAC. So this means that we have the data collection and the training operating asynchronously. We have a trainer that has a GPU, trains our models, passes those off to rollout workers that collect the data up from the PlayStation 4s. And so when we started this project, one thing we had to do was to build this big compute infrastructure. We have all these PlayStation 4s in the cloud that let us run and collect this data. Talk about the observation space. So Sophy has access to information about itself. So this is velocity, acceleration, wheel loads, and tire slip angles, those sorts of information. And we also have a projection of the course. So we use something we call course points. This is a projection of the left, right, and center lines ahead of the agent. The distance between them is scaled by the velocity. So the faster the agent goes, the larger the distance between the points. So you'll see that as the car approaches the corner and it slows down, those points will start to contract. You can think of this as an attention mechanism, essentially. And as we accelerate out of the corner, those points will start to spread out again. Action space is very simple. Continuous valued, we have mapped brake and acceleration to one output of our network and steering to another. And we have to have some way of representing the opponents. So at the time, what we did, at the time of the paper, what we had was essentially an ordering based on distance from our car of all the opponents. And then we would essentially slot those into our network inputs in fixed positions with relative position, velocity, and acceleration. Yep.
It says they're ordered by the distance from your car. So that means like if in the vector itself, like the coordinates corresponding with the yellow car on the sheet.
So the coordinates that we're using are all relative. Yeah, and so if they change positions, say if that yellow car, sorry, the question online was what happens to the observations, the features there as the cars move. So say the yellow and blue car changed position, suddenly blue was closer than the yellow, they would fall into that different slot in the input of our network. Yeah, essentially in the network inputs, that's right. But the position, velocity, and acceleration would still be relative to Sophy. Yeah. Mm-hmm.
So the position is only along the track, right? You don't follow the position.
That's right. We were ordering based on position along the center line. Yeah.
But the agent still is able to see where they're going.
That's right. Yeah, it can still see the relative position and orientation. Yeah. All right. Next point here is that a real key part was making sure that we had the right data at the right time in the right proportion. And what that meant is that we went through and hand designed a lot of training scenarios to make sure that we covered the kinds of experiences that we thought were critical for Sophy to see. So no special exploration like Marlos likes to do, just exploration by hand. So we had scenarios like 1v0, which is essentially a time trial scenario where you don't interact with any other cars. 1v7 would be Sophy interacting with 7 other cars. So on one hand, we focus on speed, going around really fast. On the other hand, we focus on making sure that we can interact well with other opponents on the track. We also had specific scenarios like grid starts, slipstream, and specific sections of the track. And all of those get put into different tables in our replay buffer. And then when we sampled from across each of those tables. And this meant that we could kind of helped us to make sure we had a high diversity of experiences always being used to train, and also helped kind of avoid catastrophic forgetting and that kind of thing. We did use some strategies like self-play, and we also played some of the opponents were the built-in AI that's in the game. These are slow, fairly slow. They're well behaved. We had line followers of PID agents that could just follow a specific portion of the track. Those kind of things that helped as well with the behavior. Yeah.
Not this slide, but I think it wasn't mentioned in the previous slide, but is latency a problem here? Like how instantaneous is the observation?
It's not really a problem. Latency is not really a problem in this. We're able to operate. Certainly, when we do training, we can operate in lockstep. And when we go to deploy this, we're actually able to run fast enough that we can just use it as is essentially. Yeah. Yeah, and we only output actions at 10 hertz as well. So, and the game itself, I think, kind of fills in some of the in-between frames for us. Yeah. So I'm coming back to this theme I've mentioned I was going to hit, which is reward design is really hard. So let's talk about rewards. I'm going to say that there are two categories of rewards. One is the true rewards. These are the things that define your problem. They do not change if your algorithm or hyperparameter changes. They are constant. They are part of the problem definition. And then we have another class I call auxiliary rewards. These are everything else. These are the rewards you put in there to help your learning algorithm. These are the rewards you put in when you have, as proxies for your true rewards, and they are part of the solution. They are the tool that you have as an AI developer to influence the behavior of your agent. And typically, these things often get mixed together, which is problematic. So our objective was to beat the humans in a 4v4 race. And not just any humans, a very specific set of 4 humans. But we can't use that for training. And we can't use that for evaluation as we prepare for these events. We don't have access to humans. We don't have, our scenarios are completely different than the kinds of laps or races that we would set up. And even if we did, getting one signal at the end of a race would be just really sparse and really hard to learn from. And I'm going to talk to you about what does it mean to beat humans in a 4x4 race. It's not just about going fast or reaching a certain position, but to do it in a way that is valid. It means you're obeying the rules, you're having good sportsmanship along the way. So the rewards that we end up using, one is progress along the course. This is an auxiliary reward. It is not the true thing that we care about. We have an off-course penalty. Again, this is an auxiliary reward. Wall hit penalty. And it is interesting, there are actually tracks, if you don't include a wall hit penalty, where Sophy learns to just ride the wall the whole way around like a roller coaster. There's a tire slip penalty, and that's there to encourage stable behavior. And then we have this thing about sportsmanship. And here's the problem. In racing, nobody can tell you what good sportsmanship actually means. There's no quantitative, discrete function anyone can give you to say that this is good sportsmanship and this isn't. And in real events, what will happen is that they will have judges who will watch the race, and when there's a crash or a collision, something happens, those judges will make a ruling about whether or not a penalty is warranted in that case. And that penalty might come 30 seconds later, it might come many minutes later. So it's not something we can use really as a signal for training our agent. We don't have access to those judges during training. So instead, we're left back in this position of trying to design auxiliary rewards. So we have a passing reward, which encourages our agent to pass and avoid being passed. And we have numerous collision penalties that we've tried to, some are really complicated, that try to capture, if you're hitting from this particular position and you have this velocity, then you're going to get a big penalty, or a constant collision penalty, which just says, here's a small penalty for any contact. Just try not to touch any other cars. And we did our best to try and find some way of capturing these concepts. And this leads us to the evaluation. So when I was in grad school, the typical thing was we would have a new algorithm and we'd want to compare it against some baseline, right? And you go off and you run your X number of seeds and you compute your mean and your standard deviation. You throw it up on a graph and you say, mine's better than this other one. That's not what we're after here. We're not comparing algorithms. What we're doing is looking for a very specific set of policy weights that produce the behavior that we want. And this is hard. How do we find that? So I gave you this whole list of different reward components that we had. And here's a problem. Let's pin that first one, progress. We're going to weight that one as 1. And we want to do this linear weighted sum of all these components to compute our final reward. How do we weight any of the other ones? There's no real ground truth to say how much more important is collision compared to progress. We don't know. And so we were left essentially doing parameter sweeps on these and running agents, seeing their behavior, looking at it visually and going, that looks good, that doesn't look good. And we ended up with this really complicated evaluation system. So if you consider each of these rows here as a separate run, these red, yellow, green, purple, as we're training, we'll save off the policies and we will compute different metrics at evaluations along the way. And then we'll pass all of those through a filtering system that does a Pareto filter. And that will give us a candidate set then of policies here. And now we put them through something we call the N-athlon. This is a whole set of hand-designed evaluation scenarios that are looking for specific behaviors in Sophy, whether it's something like slipstream or how it behaves when it's around 19 other cars, those sorts of things. Those all have associated metrics that are hand-designed, and then from that, we get a big spreadsheet. And what would be great is if I could say the top one is that's the best model. We can't say that. We don't have a fitness metric that says exactly this is the best ordering. So instead, what we would do as a team of humans would be to look at, say, the top 10 of those, compare metrics, watch videos, and try to make some guess about what we thought seemed reasonable. We would take then a handful of those and we put them through what we call the policy versus policy, or PVP. So this is mimicking that evaluation, that race that we were going to have. So this is 4 of one policy versus 4 of another policy. They go out and they complete entire races, and we score them based on their position, just like we would in the big event we had. Based on that, we get a ranking over these policies, and we take the top 2 and we feed those to the humans. And then we have people who are experts at Gran Turismo race against these agents, watch these agents, and make evaluations if they're good or not. Deepak, do you have a question?
Yeah, sure. You said after the PVP stage, you were able to input an ordering on the policies.
Yeah.
But you said they're all taken from Pareto front, right?
Yeah. So at this stage, we go through the Pareto filtering.
Yeah.
Yeah, and then we go through the N-athlons, right? And then that gives a scoring, a ranking over them. Then we have them compete against each other. And out of that competition, you're going to have that this one scored higher than this one. So you will get an ordering between them. So again, at that point, it's 4 of one policy versus 4 of another policy in a race. So when that race completes, one will have a higher score than the other one. And we do this multiple times in multiple kind of configurations and take an average and say, that one did better overall, had a higher score.
I think, again, at this stage, the final score is, it is important, but you also want to optimize the other skills that we have.
Yeah.
And they don't get filtered up with the person because one of them is bad.
Right. Yeah. Okay, so summary so far about my reward rant. So we can't quantitatively define what good sportsmanship is. And our eval scenario is unavailable and significantly different than our training scenario. There are multiple competing objectives, and we don't have a true known weighting. And the ground truth is encapsulated by the game developers. They have some idea in their heads about what a good agent looks like. And that's something that's a black box to us. So before I move on to the second part of the talk, I'm just going to kind of hit some common questions I get about GT Sophy. Can this be applied to autonomous driving? Yes, absolutely. The fundamental ideas can be applied. We have some limitations. I can crash my car as many times as I want in PlayStation 4, and there's no consequences to me there. GT is not a noisy environment. If you're in the real world, you have to deal with noise. So those are two big ones there. Why is QR SAC over SAC? QR SAC just worked better. We got better results with it. Could you use planning or a model-based approach? Sure, we could. So the kind of go-to approach right now in the field of autonomous racing is model predictive control. We tried it as well. We didn't get as good results. We got far better results using our approach here. Why don't you use screen images? As I mentioned, the PlayStation 5, just due to the limitations there, we can't use screen images. We did publish a paper last year at RLC 2024 on showing that we could use them in principle to achieve similar results. Why not learn from human demonstrations? That comes down to primarily to legal issues where we were not essentially allowed to interact with human data. Does the agent exhibit the same behavior each lap? It is a deterministic policy. So if it gets the same input, it will output the same, give the same output. The likelihood of seeing exactly the same input is pretty low, but you certainly see kind of modes of operation that Sophy will fall into. Marlos? For exploration.
So you're taking the argmax, whatever is the argmax for the.
Yeah, so our policy is parameterized by Gaussian. And so, of course, that would be noisy for exploration. When we are in exploit mode, at evaluation time, we just take the mean of that Gaussian. Yeah. Does the agent exhibit the same behavior? I just did that one. What were some of the biggest challenges with deployment? So the PlayStation 5 runs, we trained everything using TensorFlow, our models, and we have to use something called Nabla on the PlayStation 5. And Nabla is a Sony developed deep learning framework, which unfortunately has been deprecated now, so we might run into some issues going forward. Is Sony AI working on other games as well? Yes, but I can't tell you about them. Yeah. The inference time is pretty quick, so it's not very big. I don't remember how many parameters we're at right now, but in terms of memory size, it's about 50 megabytes, I think.
Oh,
yeah.
Then we said it generalizes against like 400 tracks, like
400 cars, 22 tracks. Yeah. 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 Yeah.
So you mentioned basically allowing as many collisions as needed, right?
Yeah.
But hypothetically, you're in the situation where you have to train like an agent with the cost of collision being significant, like to mimic something like human.
Yeah.
How would this change the overall?
Yeah.
Is that even going to be possible?
Okay, so the question for the audience was, if you were trying to capture the cost of collision in the training, how would you go about doing that? How would it change things? Is that possible? Need for heuristics, heuristic approaches. So, and I'll talk a bit about that maybe in the next bit here too, but you need to understand that these rewards, when we give penalties and rewards, these things interact with one another, and having steep penalties for things like that, agents tend to behave poorly at the beginning. You know, good behavior comes later. And if they see a lot of that bad behavior up front, it really discourages exploration or doing things that would eventually lead to a good solution. So it really, you have to play around with a lot of scheduling with some of these things. Is a answer, not the complete answer. Yeah.
The developer came back and said, okay, we have this expert agent, but we want various levels of difficulties. Would you first look at maybe just modifying and the outputs, so like restrict for how fast it can accelerate, or would you look at just coming up with new rewards and totally be changing how your reward layout is set up?
So we've tried. This is part of the things we've been given. The question for the people online was, if the developer was asking for different levels of complexity or capability in our agent, how would you go about addressing that? We have been asked that, and we are tasked with that. We can't talk too much about some of that. We have tried a number of things, including, you know, some things that maybe are less principled, just adding noise to the observation space or the action space. There are a lot of things you can try. I don't know that I have a great one to recommend at this point. I would be hesitant to play around with the reward too much. Yeah, playing with the reward can really impact, you get unexpected behavior. So it's not a bad idea, for sure. You just have to see how it plays out, I guess. Yeah.
You mentioned that originally you trained it was a single policy, so like this car on this
Yeah.
on that car. Now it kind of is more generalizable.
Yeah.
Do you have to change any of the state space to like let it know like it's the car to drive it to track it, that give it a lot more info?
Yeah.
That generalization, or was this more training it with more cars and tracks?
Yeah. So the question was, you know, basically, how did we achieve generalization with Sophy? I was going to save some of these for the last, but I'm gonna maybe I'll just preface a lot of my answers from here on out as, because this is an active product, I am limited in how I can answer these questions. And generalization is one of the things I've been told not to go into detail on. Yeah.
There's a question online. How hard is it to open updates to the game? Just a big frustration.
Yeah. So how do we cope with updates? Those right now tend to be breaking. We do have to retrain our agent. There are some ways that we're getting around dealing with that. Again, and pretty much anything you're asking me about the current version, I'm very limited in what I can talk about, unfortunately. If you can imagine reasonable ways of doing that, we've probably tried them. Yeah. Yeah. Okay, great question. So the question was, in the PvP part of the evaluation, does Sophy know which cars are on its team? The answer is no. No, it's essentially every car for itself out there. Yeah.
Some of the breaking changes, just as a developer, as a researcher, when you see that changes, I don't know if they're big or small change, but when you see it breaks your, I don't know how much it breaks your model, but do you intuitively think maybe there's something wrong with our approach that's not too much on that, or it's heavily relying on like pure mechanics? How do you think about that?
Yeah, so there are, when you move to a product and you have limited resources, you have to prioritize what you work on. And absolutely, we would love to address some of those issues better than we are currently doing right now. And we are well aware that there are problems with our process and that there are ways that we could handle that better. It's whether or not they make it onto the bucket list of these are the things that we're going to work on now that determines if it happens or not. Yeah.
I don't know if we're running out of time. I can save it.
Okay. Well, we'll just include this as part of the question sessions. Right. So this, yeah, go ahead. Yeah.
All of this, this is a well, I think it would be more to the growing motivation, especially the possibility of
So, So the question was that this seems like it would have been better formulated as a team setting, and whether or not we had tried that. The answer is we had definitely. So, little history. I worked on GT, then I didn't work on GT for probably 2.5 years, and then I came back to GT. So there is a gap in there of where I don't know what happened really, but I have seen in the code base that there have been attempts at formulating it as a team problem. Yeah. But actually, for the kind of scenario that the game designers are looking for, which is a separate thing from the exhibition match that we ran, they're not looking for that team kind of behavior in general. Yeah. All right. So this part of the talk is my second part of the talk. I'm actually really excited. This is the first time any of us have tried to present this work that we did. It was NERD 2022. And we had just kind of come out of work building GT, Sophy. Some of us really cared about, applied RL, and we're kind of frustrated with some of the process that we felt we wanted better tools for the agent design. And so that led us to this thing we called value decomposition. So our RL agents, that reward is typically constructed by multiple reward components that are weighted and summed together. And then we learn a value function over that. So that's the expected sum of future rewards. And if you look at the math, you can go, oh, hey, we could actually just linearly decompose that value function. We could take a value for each of those rewards and then weight them by the original weighting and sum them together and reconstruct that original value. And so that was the main idea. If we do this, this gives us better insight into what's going on with each of these rewards. So let's talk about a specific environment. This is Lunar Lander, which I'm sure a lot of you have worked with. There are 9 different components that Lunar Lander uses for its rewards. There are 5, which I consider to be true rewards. These are defining the task the actual problem you're trying to solve. And then there's a handful, another 4 that are arguably auxiliary rewards. Now, small rant is that the way Gym was released, this Gym API, it would just give you back, first they define the rewards for you, and then they give you that back as the sum. That's your R. And that's the thing that almost everyone out there, when they're comparing their algorithms, they evaluate against. This is really problematic. Because that mixes in both the true rewards, again, that's our problem that we care about, and these auxiliary rewards that have been used by some developer out there to try and shape the behavior. So it's not really the thing we're looking for. And there's work out of Brad Knox has a bunch of work out there showing that some of these rewards can be kind of overfit to particular algorithms. So now you've gone off, you've got this algorithm, this new algorithm, you want to evaluate it against some baseline, and you go out and you say, it's better than the baseline. Is it? Or is it because these rewards are better suited to your algorithm, these handful that you've designed already? And it's not well separated.
Right.
Yeah.
Where do you draw the line? We would always say that the reward is 1 when you accomplish the task, and 0 when you don't. And then at some point here, you have like reward for, and I understand that if you want to give a reward for deviating from the center, because now you're defining the task would be like exactly the center.
Yeah.
So you're making this distinction between the problem rewards and the auxiliary rewards, but like fifth, they're shaping penalty for deviation from center. Shaping almost means that it's auxiliary.
I had it originally listed as an auxiliary, and I debated that one. So I don't. So this is hard. Like, is the goal just to be between the yellow lines, or is it to be right on the center? It's probably just to be between the yellow flags. So it's not. It's more probably a proxy. But I take your point. It is hard to do this to make sure that you do it. So I would suggest starting with the true reward, identifying first what is the thing the behavior you're trying to accomplish. Going back afterwards is trickier. So Gymnasium, I'm still ranting about Gymnasium. So if you look at the API, they typically would just return that R value that's already summed up, includes all these rewards. Some of the newer environments, Mijoko being one of them, will include a breakdown of the components in the info field, which is better. But for something like Lunar Lander, we had to go in there and extract those rewards manually and recompute them. Yeah.
Sorry, maybe this is Marvel, like addition to Marvel's question. I just don't understand how there could be 5 true rewards for one goal. If you get one goal, everything else except for the one thing that you're maximizing should be accelerated.
Well, I would argue that I can take your point. Sorry, online, the point was, it shouldn't, if you have a true reward, shouldn't that be the only one thing you care about? So this is a little bit, what you're saying is kind of true, that I've been a little bit arbitrary with some of these. Is crash really part of, is it an auxiliary or is it a true reward? The thing you really want to do is land, but you also, in this case, want to minimize the amount of fuel used. So that's those first two, main and side, are about fuel usage. So it is a multi-objective problem here, which is a great kind of segue into maybe some stuff that comes up later. Is I want to argue that a lot of real world problems are multi-objective, and it is really, really hard to get a clear sense of how you balance those. How do you weight each of those objectives? We still don't have a good answer to that for GT Sophy. Okay, so what does this let us do? I said we wanted to use this as a tool. By splitting out the value function into these individual components, what does it let us do? One thing is to compute something we call influence. So this is essentially saying, how much does each of these reward components contribute to the action being chosen at the moment? Okay, and we've got this kind of proxy measure we call influence here. Oh, sorry. But if you consider these value functions across the top, so this is just a toy example where we have 2 actions, one along each axis. Maybe it's throttle brake, maybe it's steering along this one. Okay, and these are the value surfaces. In our completed summed value function we have on the left here, we have taken a particular action and we compute the gradient of that of the value function with respect to that action, and that'll be our black line. And then to compute the influence that any particular component has, we remove that component from that summation, take that action again, and we compute the gradient at that point with respect to that action. And the idea here is, if this change, this red line, if that's really large, that means that that component had a big impact on the action selection on the surface there. And if it had next to no impact, then we say it really didn't have much influence. So let's just do things like this. This is, again, Lunar Lander. And what we're looking at here is learning over time. Okay, so as we progress across our training, you can see that in the beginning, landing had very little influence on the decisions being made. This makes sense. We don't really see good landing until we've acquired some capability. Crash, this orange one, had more influence, and slowly it's starting to drop off as we train. We can also look at individual trajectories. So in bipedal walker here, our goal is to keep walking across the environment without crashing. So we have components for both of those, for forward progress and for failure. And here we can see in this particular case, we've run up against this block. Our failure component has suddenly switched to becoming the dominant thing driving our action selection right now. So we can't go forward. Let's just not fall over. So continuing on with bipedal walker, one other thing this lets us do is identify conflicts between the reward functions. So we observed that when we were training bipedal walker, if you had, say, 100 training examples, different seeds, maybe 80% of them would succeed in learning the policy within our window of training. And we observed that this failure component seemed to be kind of conflicting with the forward momentum quite often. And so what we did as a result of identifying this problem using this value decomposition was to schedule the weighting on the failure component. So in the beginning, don't put any weight on the failure component, let the thing explore. without fear of crashing, and then begin to dial that in. And as you can see from the orange line, as compared to the original blue line, this significantly improved learning performance and learning reliability. So that kind of ties into what you were asking before, Sergey, about if you had to train with collision being an important part. By doing this value decomposition, it also let us identify some problems in our environments. So we have this original return. Sorry, so this is Lunar Lander again. Because now we have the value prediction for all these components, we can plot each of those against each of their returns. And when I did this, I saw that my predictions were really good for all my components except for landing. And we see our return is this dashed blue line here that creeps up. And our original unmodified algorithm would produce value estimates that look like this, where it would plateau and flatten off there. And why? That's obviously a problem. What was happening in that case? That caused me to dig into the environment, have a look at what was happening inside, and see that Lunar Lander would only mark it as being successful landing when the velocity would remain 0 for a certain fixed period of time. So how do we resolve that? We add in this case, I added in a simple trace on the velocity, so that the agent became aware of how long it had been since it had landed, and that allows us to make the state space Markov and allows us to improve the value prediction. Still looking at Lunar Lander, we can also use this to apply some domain knowledge to our updates. So what we'd observed is when we looked at all of these value estimates, we would look at crash, the value estimates for crash. And this should always be a negative thing. It's bad to crash, right? Without modification, we would get a lot of estimates of positive value for crash. Maybe that's okay for the learning algorithm, but it was really confusing as a human to interpret what that means and why it would do that. So if you look at our usual TD loss down here, we have this left side, which includes our Q value estimate, right? And what that can be problematic. What the output of that isn't reliable necessarily, especially as we're learning. And so what we can now do is we can just clip this whole target side to say, you should never be more than 0. And when we do that, then we get better behavior here. You can see these blue lines. It's always saying that crash is bad. That's what we'd expect, right? Did this have an impact on policy learning and behavior? Not really in this case. Might it in other environments? Maybe. Okay, so just kind of almost wrapping up here. So we've got this technique. We've shown numerous instances where we were able to use it to gain insight into our learning behavior, into the observation space, into the interaction between reward components. So we probably use this all the time, right? We don't. We don't use it at all. And the reason is once we moving from a single head on our critic to multiple heads, instead of getting this awesome auxiliary learning effect where everything got better, we often got cases where learning got much worse. And the reason for that turned out to be conflicting gradients within the updates from each of these components. We applied a correction, a method called CA grad out of Peter Stone's lab. And that was great, actually. It totally fixed the problem. In some cases, it made the learning far, far better than even the baseline. Awesome. It's also ridiculously computationally expensive. And so we don't use it. So we just can't, like 85% worse or something. Like it's bad. So we have not come up with another method that solves it like CA grad does, while keeping the computation low without impacting computation. So if anyone has any ideas on there, I've tried lots of hacks and heuristics, things like scaling rewards and trying to normalize them. Those haven't worked. So in closing, I'm going to rant about reward. And I said that I want at the end of this talk, I just want you to care about reward design. Don't take it for granted that it's given to you and that you can just go out and solve everything with the given reward. Reward design is hard and it's not well studied. Some ideas around this come out of Brad Knox's research. I think he's a part of all three of these papers. He talks about the difficulties and just how bad all of us RL experts are at designing rewards, how often the rewards that we design are totally misaligned with the behaviors that we want. I highly recommend having a look at these papers. And one of the things I suggest is if you have a set of ranked trajectories to say this trajectory is better than this one, you can use that as a way to compare the rewards. You can run your rewards on those trajectories and do a comparison. Does it maintain that ordering? It's an interesting idea. So for students, I would suggest that when you are learning RL, don't use the default reward functions. Learn to define them yourself. At least don't take it for granted that they are just given to you. Use that info field that comes out of STEP for the environments that contain the different components and identify which ones are really the thing you should be comparing on. Practically, if you're defining an environment yourself, use that info field again to return those components. You can add all the reward components separated out in your replay buffers, practically speaking. For those of you who are teachers in the audience, please care about reward design. You guys are the ones who really teach the students to care about these things and to do the research on it. Give assignments that encourage thinking about that problem, even if they don't have to go through and actually solve it. Even just having to work through that thought process, I think, can be enlightening. And maybe controversial, I'm going to say that reward functions are a terrible, terrible way for humans to communicate desired behavior. They are not natural for humans to communicate in, and we have a hard time thinking through the interactions. There's been a number of works recently on using LLMs for reward design. Some pretty good results, actually. I have a paper myself that I'm working on with an intern from Mila, Michelle Ma, that we're hoping to publish soon. And you guys have already had a lot of questions, but we can take a few more. Oh, actually, we're at time. I'm going to leave you guys with this awesome video of drifting. Great. So this is really fun. This is just, we're rewarding tire slip here. Just a really simple tweak. All right, so it is noon. We have some time? Okay. I can take a few more questions. If you have them. Yep.
So I was wondering, have you considered analysis the behavior between the GT Sophy and human player? Like the GT Sophy spreads like human likeness, or because it suppresses the human players. So is the human learns directly from it, or just the skill is
Yeah. Okay. So great question. Question was, how have we done comparison between human players and GT Sophy, comparing kind of the behavior, and can humans learn from GT Sophy, or is it fundamentally different? So we have done analysis certainly on the behavior, and particularly trying to look for ways that we can capture human-like behavior. And you were asking previously about different levels of competitiveness. One of the things might be would be to try and capture behavior similar to different level players. This is how beginning driver behaves. This is how a more intermediate driver behaves. So we've done that kind of analysis, and we're certainly having a look at that. Sorry, what was the second one again? If you can learn from, yeah. So the question was, can human drivers learn from Sophy? The answer is yes. So one of the things that those pro drivers that we had racing against, they were really excited about being able to learn from Sophy, because one thing that Sophy did was to, in many cases, break the traditional racing rules. What they all get taught about certain, you should take a corner in this particular way. Sophy didn't do that in many cases. It would find some other optimal way to do it that was better. And so the drivers were learning to try and mimic that behavior. It might be harder for humans to do. For example, typically you don't try and brake and turn at the same time. Sophy's happy to do that. Yeah.
So have you considered, because like in order like in software, they also do something to limit the frequency, the activity that the AI can use. Because sometimes if the AI can do lots of action within the shorter time limit of the previous time, can do the synthesis. We consider to do some this kind of.
Yeah. So the question was, have we considered limiting the agent's behavior in some way, say with action frequency? We're actually operating slower than the humans are. We're operating at 10 hertz, and the humans can actually operate faster than that. Yeah. We also, I want to make one point clear, because this kept coming up in our nature reviews, is we didn't set out to make an agent that had the same limitations as humans. It wasn't meant to be fair in that sense. It was meant to be an agent that we could finally put it in the game that would be at a level that was competitive for these players to play against. So in that regard, we use any tricks that are available to us to do that. Yeah.
We're trying the influence of each reward.
Yeah.
Is there a reason to believe that it would or wouldn't be agnostic to the loading algorithm, or would you find that those relations would be quite different if you go from one to the other?
So meaning like PPO versus SAC, or the influence would change. That's, sorry, the question was, do we expect something like this? Are you talking this one here? Maybe these influence levels to be different depending on what algorithm we were using. I think based on some of Brad Knox's work, I would say probably. Yeah, he did have some interesting work that showed that some of these reward components just work much better with depending on what your underlying algorithm is. Yeah.
The same addition to the question, but I fail to see why. Like if you have a converge like function, why would the component be different?
Converge though, you just
okay.
Right. But I think that's the key. Is at the end of the day, we don't just magically get to converged. We have to go from 0 to converged, and I assume that it's that path through that process that's harder to navigate for some reward algorithm couplings. Yeah.
I think on the next slide is a graph. One more.
Okay.
Yeah.
Yep.
This graph on the right. It
Yeah.
looks like the variance in the schedule weighting is a lot higher. Was that concern if you have that of the schedule weighting method, or is that not really a concern? It's just dramatically more successful?
It is dramatically, yeah, we're not really concerned about it. I mean, the intervention had the desired effect that it made it much more reliable. Is there still variability in that? You're right, there is. Yeah. All right, well, thank you, everybody.